Now what I have here, it's a heating curve. So let me write it down. This is just a graph that is showing you how the state of a substance will be changed as the amount of heat is added. So if we start increasing or adding heat, the temperature will start increasing and a substance can be converted from one physical state to a different one. So that's what it's been representing right here. Now this graph corresponds to 1 gram of water. So I'm going to start by pointing out at two temperatures in the y-axis. We have 0 and we have 100. Those two temperatures are identified. So you see the temperature is increasing in that y-axis. And the temperature is increasing because the amount of heat is also increasing. And amount of heat is what I have right here. So as the heat is added, the temperature increases. Now, this graph is for water. So 0, it's a temperature. That's the melting point for water. The melting point for water represents the temperature at which water goes from a solid to a liquid. So in that graphical representation, the blue line is representing the physical states. So in the graph, this line that it's below 0, you see where the 0 is starting, it's right here. That's your 0, which is the melting point, or MP. The physical state that you have for the water right there is a solid. So you have water, 1 gram of water as a solid. As you start adding heat, the temperature of the water is going to start increasing. Now your solid will be converted to a liquid. So in this part of the graph, where the line is flat, see that line, it's completely aligned with your axis right there. That part is representing the phase changes, your solid becoming a liquid. So this here, it's a solid plus liquid. You have both states in that part of your graph. Now what's happening is that your 1 gram of water, it's absorbing heat, right? So it starts melting. So it will become a liquid when everything that you have as a solid, it's actually melted. So not until everything is melted, you don't see the line increasing again. So what is happening in that flat line is that The amount of heat that it's being added to your 1 gram of water as a solid, it's being used to actually break the attractions that you have in the solid state between the water molecules. So the temperature is not increasing. You see, you have a flat line where you have solid plus liquid. The temperature is not increasing because the amount of heat that is being added, it's actually breaking attractions between the water molecules. That amount of heat is not being used to increase a temperature. It's used to do something else. Now, when all of the attractions between your solid particles in your water are being broken, now you keep adding heat and the temperature starts increasing again. That's why I have what I have represented in that line. In that line, all of your solid was melted and now you do have a liquid. So when heat is being added in that liquid state, the temperature keeps increasing, increasing, increasing until you reach another part of your graph where you have a flat line, which is that part right there. That flat line or that part in your graph where the temperature remains constant, that's what the flat line represents. The temperature remains constant. If you look at the temperature in the beginning of your line, 100. If you look at the temperature at the end of the line, still 100. So the temperature is not changing. That part in your graph represents a combination of two physical states. Your liquid is being evaporated right there. Your 1 gram of water, right, starts absorbing heat from a temperature above zero, absorbing heat all the way to 100. When the amount of heat that is being absorbed, it's enough to reach 100. Now the liquid starts evaporating, and in that line where you have a constant temperature at 100, what is happening is that the attractions between your particles in the water, right? For your water to be a liquid, it needs to be, your molecules are attracted to each other. So the amount of heat that is being added now, it's used to break apart those attractions between your water molecule. So the water can actually go from a liquid to a gas state. That temperature right there represents the boiling point of water. Is the temperature that it's required to actually evaporate water. Not just 1 gram of water. Melting points and boiling points, they don't depend on amount of substance. Melting point and boiling point. The melting point for water, it's always zero, regardless of if you have 1 gram or 100 grams. Melting points are example, a melting and boiling point, both of them are examples of intensive properties, which are physical properties that are not dependent on the size or the mass of your sample. So melting point and boiling point is not just for 1 gram of water, it's for any amount of water. Now looking at the graph, when the temperature starts increasing, you have your at 100, right? Your liquid is being evaporated. Now when the temperature starts increasing above 100, the line in the graph starts increasing too, going up, not flat. That part right there represents a gas. All of the water is evaporated, and now the amount of heat that is being added is used to increase the temperature. Since this is for 1 gram of water, we can actually write down numbers for the changes in state right here. The amount of heat added for your solid to become a liquid, it has to be 334 joules. So this line right here, amount of heat from that point to this point is 334 joules, which is the heat of fusion of 1 gram of water. Now the amount of heat that is required for your water to become a gas is the heat of vaporization from here in your graph all the way to here. The amount of heat that is being added is 2260 joules. What I drew right there is 4 molecules of water, and then I'm connecting all of them with dash blue lines. Yeah? So what I'm trying to show you here, it's how the amount of heat that is being added into your water is being used to break apart the attractions between molecules and not to increase the temperature. So when you have your 4 water molecules, and this is a very small representation for the number of water molecules. If you have 1 gram, you have many more molecules than just 4. But when you have 1 gram of water and your water is in a solid state and it's being converted to a liquid state, which is the part in your graph with those 334 joules of energy. That amount of energy is being used to break apart some of these interactions here, or some of those attractions for your between your water molecules. Now, when you move in your graph up all the way to that line where you have 2260 joules of energy, that amount of energy right there represents the amount of energy that is required to break apart all of the attractions between all of the water molecules. That's why your numbers are so different. Even though they represent the amount of energy that 1 gram of water is being absorbing, it's different because the number of interactions between your water molecules for your solid to become a liquid that needs to be broken or pulled apart, it's smaller than the number of attractions that you need to break for all of your water molecules to be apart from each other to go from a liquid to a gas state. So 334 joules represents an amount of energy to break some of the attractions. 2260 joules of energy represents an amount of energy that is required to break all of the attractions between the water molecules. So when the line remains flat in your diagram, that represents that absorption of heat that it's required to break apart interactions between your water molecules. Those interactions are physical interactions. There's no breaking of chemical bonds in here, because all of this is representing physical changes. So one last thing here, and I'm not going over all of this, you have a table with all the terms that we use to refer to these phase changes and what's happening to the temperature. So just for example, melting fusion, both terms are representing a phase change from a solid to a liquid, and for that to happen, those are endothermic processes. The temperature is increasing. In this table, whenever the temperature is represented with an arrow pointing up, that represents an endothermic process. Arrow pointing down, that represents exothermic. Amount of heat it's being released in exothermic, amount of heat it's being absorbed for endothermic. At the end of the table, I have two terms that probably were not too familiarized with them: sublimation and deposition. In general, we know what melting, freezing is, boiling, but sublimation and deposition, these are a phase change that is not passing through a liquid. Okay, so we're used to see solid to liquid, liquid to gas, but a solid can actually become a gas without passing through a liquid state. That's sublimation. And a gas can become a solid without passing through a liquid state, and that will be deposition.